Welcome to Miss Prince's Physical Science Connection. Today's episode is a review on light waves. In our study of waves, we looked at the types of waves, the characteristics of the different types of waves, the properties that we can measure, and the different behaviors of waves. But before we go into that, let's first define what is a wave and what it transfers. So when we talk about waves, we have to remember two things. Waves, they transfer energy, and they're nothing more than a disturbance. All right, there are two different types of waves. You have mechanical waves and you have electromagnetic waves. Mechanical waves require a medium, while your electromagnetic waves do not require a medium. Now, mechanical waves, because they require a medium simply means that they need some type of matter, solid, liquid, or gas, in order to help transfer the energy from one place to the next. And mechanical waves can either be transverse waves or they can be longitudinal waves. And then you have electromagnetic waves, which are just transverse. The characteristics of transverse and longitudinal waves are actually quite different. As you can recall, the highest point of a transverse wave is called a crest, while the lowest point is called the trough. On a longitudinal wave, your area where the energy or the wave is compressed is called a compression, and where the wave is spread out is called a rarefaction. Now, while transverse and longitudinal waves are different due to their characteristics, they both have the same measurable properties. All right, when we are looking at the properties of each wave, we can look at wavelength, we can look at frequency, amplitude, and speed. The wavelength on a transverse wave is simply from one corresponding part to the next corresponding part. So it can be from crest to crest or trough to trough. On a longitudinal wave, the wavelength is simply, again, from one corresponding part to the next corresponding part. So we can go from one compression to the next compression and one rarefaction to the next rarefaction. Frequency is just the number of waves that pass in a given moment of time. For instance, you can have 4 waves per second, 10 waves per second. So just depending on the number of waves per second will tell you how frequent the waves are occurring. Then the amplitude looks at the amount of energy in the wave. In a transverse wave, that is pretty much from the equilibrium or rest position, which would be just midway through the wave, and then from that point to the crest or from that point to the trough. Okay? And then in the longitudinal wave, when you're measuring the amplitude, you're looking at how tightly compressed or how stretched out the sections of the wave are. So here, these compressions are not as squeezed together as the ones at the bottom, and these rarefactions are more spaced out than the rarefaction in the wave at the top. Again, that looks at the amount of energy in the wave. The greater the amplitude, the more energy. To determine the speed of a wave, all you have to do is multiply the wavelength times the frequency. Regardless of what you have in a wave problem, you look at what you have to find and you use what you've been already given in order to determine what part of the math equation you're going to use, or how to set up the math equation rather. Again, so here's the triangle I've given in class. We have the V that represents the speed, we have wavelength, and we have frequency. So speed equals wavelength times frequency. If we are looking for the wavelength, then Typically, we are usually given the speed and the frequency, and we know that we're going to divide the speed by the frequency in order to find the wavelength, and so forth and so on. Same thing for frequency. If we're looking for frequency, we're just going to divide the speed by the wavelength in order to find the number of waves that are passing in a given amount of time. There are 4 ways in which waves behave. The good thing about waves is that they behave in predictable ways. They either reflect, refract, absorb, or diffract. When waves reflect, it just means that the wave is bouncing back. It's not able to pass through whatever is in its path. It also means that the wave is going to reflect at the same angle that it's incoming as outgoing. Refraction occurs when the wave moves from one medium to the next, and it causes the speed of the wave to change. So the wave could be traveling this way, but once it hits that medium, that could change its angle. And of course, once it gets past that medium, if it goes back into where it was originally, it can pick up its original angle. All right, so refraction just means the bending of the wave. The absorption of a wave means that once the wave is absorbed, it's taken in, it's not, it can't come back out. It's kind of like a sponge that absorbs water. It soaks up the water, and you don't see the water running through the other side as it's trying to pass through. So that would look just like this. And usually in this case, we would like to think of concrete. When the sunlight hits the concrete, what do you notice happening? All right, you should have said that it starts to heat up. So we can say that the light energy is then transformed into thermal energy. The final way that waves behave in a predictable manner is through diffraction, and diffraction simply means that the wave is going to move around a barrier, or it's going to travel through an opening and then continue to spread out. All right, so earlier I said to you that there are 4 ways that waves behave in a predictable manner. Now, we know that there are plenty of materials out there, but every material is different, and depending on the type of material will determine if the wave is going to pass through, slightly pass through, not pass through at all. So when we look at transparent materials like saran wrap, or what you may call as clear wrap, you can see through that object, and so as the light hits it, the light passes right through without any issue, and you can see with fine detail the objects on the other side of that material. Now when you look at translucent materials like wax paper, the light is also still allowed to transmit, which is another way of saying passing through. It's allowed to transmit, but however, the light is scattered. So then you're not able to see things with fine detail. You can make out that there's an object there, but again, you're not seeing the exquisite details. Then you have the opaque material like aluminum foil and concrete. And you have 1 or 2 things that can happen. If it's a material similar to aluminum foil, then the wave is going to hit it, but it's going to reflect back, again in the same angle that it's hitting the object, okay? You're not able to see through that material at all. And then if you have something that's similar to concrete, instead of it reflecting the wave, it is absorbing the wave and turning that, or transforming that wave energy into thermal energy. So these are the 3 ways in the 3 materials rather that light waves have to interact with, and depending on the type of material will determine what's going to happen with the wave. Okay, so in the second part of this light waves review, I will cover the electromagnetic spectrum and looking at the different frequencies from low frequencies to high frequencies. And then we're going to look at light and color, how we're able to see certain wavelengths and why we're not able to see other wavelengths, and how we can mix colors in order to come up with other colors, so primary and complementary colors, and how that differs from pigment color. And then we will also cover how the eye uses light in order to see objects.